So, hello everybody. My name is Anish Raj and I'm from the Friedrich Schiller University in Germany. And today I'm going to be talking about my paper that I submitted for the MIUA 2020 conference. So let's get into it. So the title of my paper is Automatic and Objective Facial Palsy Grading Index Prediction using Deep Feature Regression. Now, the aim of the project was to grade the condition of facial paralysis based on a complex grading system that is the eFACE grading system. Now, there has been previous work related to this field, but most of those approaches were highly dependent on detecting facial landmarks, which are difficult to detect properly for facial palsy patients, as they have gross asymmetry in their face, and there's not a big amount of data set that is available that can be trained for these landmarks. And then the second point is that most of these systems use less sophisticated scales like House-Brackman, which has only about 6 grades, and they are very easy to predict in comparison to the eFACE, which has about 16 parameters to predict. Now, at first, I would like to talk about a little medical background behind facial paralysis. And as you can see on the left-hand side, the facial nerve emerges from the brain. And in fact, we have 2 facial nerves, one for left-hand side and another for the right-hand side of the face. And as you can see, it divides into 5 different branches to control different muscles in our face. On the right-hand side, you can see a sensory nerve that runs along the facial nerve, and it controls the functions of glands in our face. So if something wrong happens to the facial nerve, it can also affect the sensory nerve, and in turn that affects the glands. So our saliva production or tear production may be affected too. And now usually facial paralysis occurs when there is a damage to the nerve, or there is not enough electrical signal coming from the brain. So if there is a damage of the nerve over here in the temporal branch, then we will not be able to move our forehead properly, and so on. So there are 2 kinds of facial paralysis. One is central facial paralysis, and the other one is peripheral facial paralysis. In central facial paralysis, there is only the lower half of the face affected, and as you can see, the upper half as well. In peripheral facial paralysis, the whole of the one side of the face is affected. So the peripheral facial paralysis occurs due to malfunctioning in the pons region of the brain, and the central facial paralysis occurs due to malfunctioning in the cortical region of the brainstem. And some of the causes of facial paralysis are stroke, tumors, face injury, and so on. Now, I would like to talk about the eFACE system that we used for this project. So the eFACE system was developed in 2015 at Harvard Medical School. It consists of a total of 16 parameters, 5 for static, 7 for dynamic, and 4 for synkinesis. And we are not considering synkinesis in this project because it can only be observed in video, and we are only using images. So we are only considering static and dynamic parameters. And then the eFACE produces an overall disfigurement score between 0 and 100 at the end. So here's an example of a patient that has gross asymmetry in her face, and she has the worst case of facial paralysis. And here are the scores: static score, dynamic, and synkinesis score. And as you can see, she does not do well in almost all of them. And there are some parameters that range from 0 to only 100. And there are some that are ranging from 0 to 200. And the ones from 0 to 100 have, in that case, 100 is the normal value, so a healthy patient, and 0 is worst facial paralysis. And from 0 to 200, those numbers, 100 is the normal, so the balanced position. In her case, the balanced position would be the balanced eyebrows, so she would get then 100, but 0 or 200 are the extreme cases, so maybe the eyebrow is lower than the normal eyebrow, or it's higher elevated to the normal eyebrow. Then she would get 200. And here's an example of how the annotation works. So this is an example of brow at rest, so the static parameter of eyebrow. And on the left-hand side, you can see she has facial paralysis over here. And this is the normal eyebrow. And the affected eyebrow is lower than the normal eyebrow, so she gets a score of 0. Here, the eyebrows are balanced, so she gets 100. And here, the eyebrow is elevated, and this is the affected side. So she gets a score of 200. Now let's talk about data sets and experiments, the main part of our project. We have two data sets. One is the control data set, another is Guntinas data set. Both of these data sets come from the University of Vienna hospital in Germany. And so the first control data set contains 28 healthy subjects, and they have 9 images per subject. The second data set contains images from 51 patients. Each patient has 2 folders for 2 different time spans, and each folder has 9 images per patient. So, and as you can see, here is one of the co-authors of the paper, and this is how the 9 images look. The first image is for the static cases, all the 5 parameters. Then you have from 2 to 9 different motion exercises that one has to perform according to the eFACE guidelines. So something like raising the eyebrows or closing your eyes. And then we use these images to predict the parameters. It is worth noting that we only use the static image only for static parameters, and then the relating images to the dynamic parameters we use for that dynamic parameter. So let's talk about the pipeline that we used in this project. First, we have an image data set combined of those healthy and patient data. Now we divide the image data set. We do the cross-validation, 11-fold cross-validation, and a little pre-processing that involves cropping the face. So we don't need background information, just the face. And we make a square image of 224 by 224 while maintaining the aspect ratio so that it is easy. So then these can be fed to the neural networks, the deep convolutional neural networks. And then the feature extraction part comes. So here's an example of VGG16. We also use different architectures like ResNet, EfficientNet, MobileNet. But here, just for an example, we use VGG16. And we extract features from layers like conv21, conv22, and so on. So all these convolution layers and pooling layer at the end. And then we take these features separately and train the linear regressor, a support vector regressor, and we obtain predictions. So this is the whole process that we do, and we want to see how these features help in prediction and what are the impacts of different architectures. Another thing is that we train these architectures on 2 different data sets. So we also want to see how different data sets can influence the predictions. Now, here are some results. So at first is the layer influence, and this is from a network, VGG16 network that was trained on faces data set that contains about 3 million face images. And this was one of the best results that we got. And as you can see, with increasing depth of the layer, we get better result in mean absolute errors. So you can see the fifth convolution layer gives us about 22 units of absolute error. And this is because as we move deeper into the layers, there more higher features are extracted from the images, and then it makes it easier for the regressor to predict from these higher features. And then we also have these results from various architectures. As you can see, ResNet 50, MobileNet, EfficientNet, VGG16, VGG faces. Now, all these first four are trained on ImageNet. So ImageNet, we all know, is trained on about 14 million images of various objects from our daily life. And the last one, VGG faces, is only trained on faces model containing 3 million images. And as we can see that the average mean absolute error of these network is okay. ResNet does not perform well, even though it's very deep, but we didn't have a big enough data set anyway. And as you can see, the faces model outperforms all of them. And it's natural because our data set is also made up of faces, and this is a more similar domain. So we would expect VGG faces to outperform other models that are trained on ImageNet. Now, these are some of the box plots from the static parameters that was obtained from VGG face model. And here you can see that most of the median values are close to 20, so they are pretty well. Here, the dynamic parameters, and again, you can see most of the median values are below 20 or about 20, not for brow elevation, which did not work well, but how most of these parameters are predicted well enough in the range considering the small data set that we have. At the end, we also conducted a control group evaluation where we trained the system again with 11-fold cross-validation containing both control and patient images. And then we just obtained results for the control group. And we found that the average mean absolute error is about 12, which is a good result considering that there is, we thought that all the faces are symmetric, so we gave them the score of balanced or 100 to all the parameters, but this is not the case in reality because there is always some asymmetry, and we found that using a tool called Emotrix, we found that average distance between left and right eyebrow and pupil is about 5.93%. So it differs by 6%, and so this makes sense. And this result of absolute error of about 12 is acceptable in that case, considering the asymmetry. Now, at the end, we have some conclusion. We see that deeper networks don't perform better, like ResNet 50, and this is because ResNet 50 has much more parameters than VGG when the fully connected layers are removed, and our data set is not big enough to train on such larger network. Second, VGG faces model outperforms the ImageNet models, and it's natural because it is more related to our application. Third is that control study shows that model performs well for healthy patients, and even though they have some asymmetry, but it's natural, and we got good results on that. And fourth is that there could be a further improvement. We think there would be a further improvement in the results if we use a larger data set of the patients. Here are all the references, and I would like to thank you all for attending my presentation, and I wish you all the best. Thank you.